Hi, hello, and welcome to the session number 10 on machine learning. And I'm surrounded by a beautiful bunch of folks who will give you some interesting presentations about papers in this session. You probably heard this in the other sessions you attended before, but you can ask questions on YouTube. There's a chat feature on YouTube, or you can also go to Discord. There's an extra channel called FP10 Machine Learning, and you can ask questions there. And I will be kind of your question speaker. So whatever you type there, I will try to pronounce as good as possible and ask the speakers after we watched their presentation on video. And we're going to start with paper number 1. And Subhajit Das actually recorded a video or will present Questor, an interactive construction of objective functions for classification tasks. See you after the talk.
Hello everyone, thanks for watching my talk. I'm Subhajit Das, PhD student from Georgia Tech, USA. Today I will talk about our paper, Questor, interactive construction of objective functions for classification tasks. Over the years, machine learning has impacted almost every aspect of human life, solving complex problems in various domains. Solving for such diverse use cases, the machine learning community has developed many algorithms. Each of these algorithms have one thing in common. They are driven by some form of objective function, which are also called loss functions. For example, in a classification task, an objective function may specify that the model should perform well on a chosen class, or may require a model to get certain data instances correct. Typically, these objective functions are constructed by data scientists or machine learning practitioners by writing code. However, such objective functions are hard for users to specify as they are a specific mathematical formulation of their intents. In addition, there is no interactive graphical user interface that can bypass writing codes to construct these functions. This not only limits the inclusion of end users to specify their goals to a machine learning algorithm, but also inhibits users to quickly prototype and experiment with multiple variants of such functions. In this work, we made construction of objective functions interactive by creating a visual interface. Our technique supports interactive specification of objectives, constraints, and weights to these functions, and then translating the function terms such that a model solver can interpret. Interactively and iteratively, users can add, remove, and adjust objectives and their weights to inspect how the function solves the underlying modeling problem. In Questor, we are optimizing to select best models as opposed to optimizing the internal logical processes of a machine learning model that makes Questor model agnostic. So using Questor's workflow, users can construct an objective function which is fed to an AutoML model solver. This solver creates n classifiers and utilizes the user-specified objective function to select the best model for the task. Our technique uses an iterative model construction and evaluation workflow. Questor empowers users to interactively construct an objective function which is fed to an AutoML model solver such as HyperOpt. In this pipeline, we pre-specify a set of learning algorithms and a set of hyperparameters for HyperOpt to construct models. Per iteration, HyperOpt consumes the user-specified objective function to construct and rank a set of new classifiers in its model selector module. Each of the classifiers are evaluated and ranked by the model selector based on their performance on the supplied objective function. Finally, HyperOpt reports back top k best classifiers for Questor to visualize. Next, I will present Questor's user interface that allows construction of classifiers on a tabular data through the specification of interactive objective functions. The major components of the interface includes a table view, a set of confusion matrices, a model interpreter view, a rule panel showing a list of rules that creates various objectives, and the objective function view that visually represents an objective function. The table view shows the training and the test data on the left. The parallel coordinate view on the right allows users to sort, search, and filter the data. Users can construct machine learning models to see confusion matrices of the training and the test set. The red cross icons show the incorrectly predicted labels of the target variable. The model interpreter view allows users to inspect multiple classifiers. Models are shown as a parallel coordinate or a star plot view, which allows where each axis is a specified objective. Clicking on a model's name on the top updates the table view with its predicted output. The objective function view lists the specified set of objectives and constraints. Users can specify objectives by interacting with the data in the table view or by clicking any of the shown objectives in this objective function view. These objectives can be added or dragged or removed on the fly, then weighted to specify their relative order of importance. We first investigated the design space of the set of objectives and constraints that can be interactively specified to a model solver to construct classifiers. Using an affinity diagramming approach, we studied over 60 research papers from the literature, based on which we categorize objectives into 4 categories: instance-based, feature-based, train objectives, and test objectives. I will discuss only a few of these next. To know about all of them, I recommend please read the paper. To understand these objectives, consider the employee salary dataset from the city of San Francisco. Every row in the data is a job type, such as attorney or nurse. The data contains over 22 attributes, such as salary, dental benefits, overtime, etc. Instance-based objectives are specifications that users can make based on the data items in the training set. The similarity constraint captures the degree of similarity or difference between data items. In this data, a user may specify a set of similar job types, say a manager or an administrator, and in doing so, the user may expect them to be predicted in the same class. Various systems in the past have sought similarity between data samples. For example, Thomas et al. In their paper discusses similarity metrics to infer if an object A is similar to B or C. In Questor, users can specify similarity through a drop-down selector and then directly selecting data items from the table view. The critical constraint lets users specify a set of data instances to show that correct prediction of these are critical for them. For example, in the salary dataset for a user, the correct prediction of a job type with medium retirement benefits from 2012 to 14 may be of more value than other data items. In the literature, a popular classification algorithm called LINE reports a model's performance based on a set of critical data instances. Feature-based objectives are specifications that users can make about the columns or the attributes of the data through the parallel coordinate view. They can specify features that are highly correlated or that are highly variant in relation to one another. The objective function will penalize or reward the model, respectively, if those features are used. And finally, users can specify a set of hand-chosen features. Models will be rewarded if these features are used. Next, I will walk you through a demo of Questor, emphasizing how users can interactively construct objective functions. Megan is a public policy analyst and loads the salary dataset with 10,000 job types as data samples with 5 class labels of department for each job types. They construct a classifier to check the base performance as a set of train and test confusion matrices on the right. She sees the red cross icons to notice that there are many samples that are incorrectly predicted. They specify a set of data samples with medium retirement benefits from the year 2015 and 16 as critical by filtering them using the parallel coordinate plot on the right. They can record any constraint they specify as a rule to review later in their analysis process. They review the objective function to check the specified objective critical. They also review a set of classifiers to see how the models has been constructed. Next, they specify the constraint candidate on a set of data items of the label cultural because many data instances were incorrectly predicted in that class. They construct a new set of classifiers to see the updated objective function score. They see that the performance improved slightly on the training and the test set. Next, they look at the scatterplot metrics to find a set of job types with exceptionally high salary, which are outlier and noise in the data. They filter the table using the feature panel and then specify a set of data items as ignore constraint. Megan looks at the rule panel to see that every constraint that she has specified is recorded as a rule. Next, Megan constructs new classifiers to find that the model is grossly overfitted. It has 99% training accuracy but only 48% test accuracy. She specifies a set of test objectives to update the objective function and next constructs a new set of classifiers to review the performance of the models. Finally, happy with the model, she exports it for further analysis. We conducted a qualitative and quantitative evaluation of Questor to validate its effectiveness. Apart from using a visual interface such as Questor, there are two other methods to create classifiers. One is by writing code in Python or R and running them via command line interfaces, which we also refer to as CMD interfaces, or directly using AutoML platforms such as AutoVeca or OrangeML. We experimented with 16 participants with some background in machine learning. We compared Questor with CMD and standalone AutoML. Our dependent variables were task completion times, model accuracy, and constraint satisfaction score. For the quantitative evaluation, we asked participants to specify a set of pre-specified constraints on the salary dataset containing 5,000 data items. For the qualitative evaluation, we asked participants to freely explore Questor and construct objective functions on the IMDb movies data containing 5,000 movies, with a goal to improve the classifier's performance. We studied qualitative feedback from a post-study open-ended questionnaire in addition to the video and audio recordings of the participant screen. We observed that participants found Questor allowed them specification of meaningful constraints via objective functions. One participant said, "I think the constraints make a lot of sense to me. When I test models, I frequently look at specific data items to verify if the classifier modeled the data correctly." They also seem to find model interpreter view intuitive to inspect models in relation to how well the model addressed the specified constraints. However, on the con side, we observed that participants specified conflicting constraints. For example, at times they specified the same data samples as examples to ignore and similarity constraint. This caused confusion to the model solver in selecting the right model for the user. A few advanced participants expressed that they were uncertain about the underlying modeling process as it was not transparent enough for them to address the models further. Quantitatively, we found Questor is easier and faster than CMD based on Likert ratings and log data of task completion times. For various subjective aspects such as intuitiveness and learnability, participants slightly preferred Questor than CMD. Further, we also found that Questor addressed subjective user constraints in the objective function better than standalone AutoML, though it produced marginally less accurate models than standalone AutoML. Questor employs a feedback loop between the user and the system to communicate intents and to inspect models. Further, we observed that in a multi-objective optimization problem, satisfying every objective might not be feasible. Thus, formalizing user goals as an objective function facilitates understanding various trade-offs in model selection. Thanks for listening. With that, I end my talk. I'm currently in the job market, so please feel free to contact me at my email.
Okay, so please, thank you very much for the talk first. I know it's pre-recorded, it's a bit weird, but please feel free to post questions in YouTube or Discord. Until that happens, I have a question from my side, and it seems to me that Questor is actually operating on two sides. So it's operating not only for the objective function, which seems to be the last two out of the three panels we saw, but it also works on the data, on the instances themselves. Yeah. So that the question that I have attached to this is it first, how common is it that you have two different objective functions for training and test? Because I have the impression you normally try to have the same objective functions just on two different sets to see, like, for effects like overfitting, etc. And the other thing is, don't you undersell your your paper by not mentioning that you also allow kind of a shallow data filtering for better generalization, etc., etc.
Yeah. Thanks for the question. So yeah, I think Questor allows users to specify an objective function. But in general, the objective function is just a single function. It is applied to both the training and test set, essentially because the objective function is used to select models that work best on the train and test set. So that kind of answers your first question in the way that we do not have two separate objective functions. We do have only one, and that objective function is essentially multi-objective objective functions. So each objective function may have multiple objectives, and some of those objectives may be catering towards a training set, or some of them may be catering towards a test set. So that's the first part of the answer, the question. The second part is, yeah, we do have another aspect of Questor, which is data exploration. Essentially, users can filter the data, find subsets, find outliers and noises, and so forth. We wanted to have a one system where basically users be able to do all these operations and be able to specify objectives. But moving forward, the real contribution of Questor is that the users would be able to interactively specify an objective function. We can assume that the users can bring in data or subset of data using other tools like Excel, Tableau, or something else. But Questor would always be able to incorporate those specifications in the form of translating those specifications in a mathematical piece that an AutoML model solver can ingest.
Cool. Thank you very much. It's amazingly great work. And there's one question from Daniel, who asks the machine learning question, I think, is, do you plan on releasing Questor openly?
So it was a test prototype for research work. It worked well in terms like it does what it promises. And also we did a study to understand how users are able to work with it, how comfortable they are, is the usability and the user experience good enough to be to move forward or not. So currently we have to work a little bit more on top of Questor to ensure that it's able to address other data which may be a little bit larger in size or may have a lot of different variables which we haven't tested yet. But yeah, in future that can be a good possibility that we have Questor open sourced.
Great. Thank you very much, Subhajit. Great presentation. Thank you for the answers. And for me, it's now time to wear a new hat. So the next one is a special pleasure to introduce. It's Fritz Lectures presenting his work on peaks, an interactive visual pattern search in sequential data using unsupervised deep representation learning. By the way, it's best paper candidate, so good luck.
Visualization and computational biology, then hence multi-scale visual pattern exploration in genomics. We are going to present peaks, equal for interactive visual pattern search in sequential data, that uses unsupervised deep representation learning. Peaks, equal for interactive visual pattern search in sequential data, that uses unsupervised deep representation learning for similarity comparison. Visual searching for patterns in sequential data can be challenging. We must search spaces large. The patterns are complex. Or the query is difficult to formalize. To overcome
So, hello, back again. We just have some audio problems. I'm waiting for the admins to let us know when these are solved. Meanwhile, oh yeah, people are complaining about the sound, so this is okay. So meanwhile, Fritz, I'm pretty sure you have backup slides. So, no, just kidding. No way for panic here. Okay, I'm trying to see if there are some questions coming up. Okay. So I just got the advice that we actually will run Fritz's talk a little bit later. So if we are switching to presentation number 3. So Michael Gleicher will present his paper, or his and his colleagues' papers, on Boxer, an interactive comparison of classifier results. Let's see how the audio is in this video.
Hi, I'm Michael Gleicher, and this video will present our work on Boxer, a system for comparing the results of machine learning classifiers. This work was done with Aditya Barve, Shinyi Yu, and Florian Heimerl, who all work with me at the University of Wisconsin-Madison. Boxer is a system for examining and comparing the results of machine learning classifiers. It allows for flexible, detailed comparisons of classifier results by enabling users to identify subsets of instances and compare the performance on them. Boxer allows a user to combine multiple views and connect them with flexible selection mechanisms. Let me explain what I mean by classifier result comparison. A classifier takes a data instance and predicts a label for it. For now, we assume the labels are a discrete choice. Classifiers are built by training using a set of training data with associated labels. Classifiers are tested by taking a test set with known labels and comparing these ground truth labels with the predictions made by the classifier. The outputs of the classifier are the results. Sometimes it is useful to examine the predictions on the training set. This is known as resubstitution. But usually, classifiers are tested on a separate testing set. The predictions made on the testing set are the results of the classifier. We use them with the corresponding test data and ground truth answers to assess classifiers. To compare multiple classifiers, we examine their results on the same testing set. This is the problem that our system Boxer considers, comparing the results of multiple classifiers. The input data to Boxer are the results from each classifier, as well as the test set data including the ground truth answers. Note that Boxer does not consider the internals of the classifiers. It treats the classifiers as black boxes. Boxer focuses on the results of the classifiers, complementing approaches that consider how those results are computed. There are many reasons why comparing classifier results may be useful. The most common is model selection, where we try to pick the best one. But comparing classifiers is also useful in places where contrasting models can help provide better understanding of the classifiers and data. Related work on model comparison falls into 3 categories. One body of work considers comparing the internals of classifiers. This work is specific to particular classifier types. Boxer complements this work. A second body of work provides detailed tools for examining a single classifier's results. We extend these ideas from this work to problems of comparison. A third body of work provides metrics for comparing models. We build upon this work to allow for more detailed inspection. Metrics provide concise summaries of classifier performance. A simple metric for classifier performance is accuracy, the percentage of items the classifier gives the correct answer on. We can choose different metrics that summarize the performance in different ways. This raises the challenge of metric selection. And, even with a well-chosen metric, it tells us little about which items the classifier is getting right or wrong. Metrics are usually computed over the entire testing set. Metrics give a concise summary of performance, which allows for easy comparison between classifiers. However, for richer comparisons, metrics do not provide enough detail. For example, we might want to know if different classifiers get the same items wrong. We might want to know if there are any items that many classifiers get wrong. We might want to assess the performance on a key subset of the data. Or we might want to connect errors to the underlying data. There are many possible comparisons we might want to make. Our goal in Boxer is to support detailed comparisons in a flexible way in order to consider a variety of questions. The main idea behind Boxer is to consider subsets of the data as a way to make a comparison across a set of classification results. A metric, such as accuracy, divides the data into subsets that are counted. For example, accuracy divides the data into correct and incorrect sets. By selecting subsets of data, we can see where else these instances occur in other subsets. For example, by selecting the incorrect instances in one classifier, we can see if other classifiers get the same instances incorrect, or if those instances have any particular properties in a data view. Conversely, we can select items in a data view and see how they connect to performance. Boxer is based around two key concepts that allow the user to flexibly perform classifier result comparisons based on sets of the data. The first is the concept of a box. A box couples a data abstraction, it contains a set of items, with a visual abstraction that displays information about those items. The second key concept is the concept of a selection. A selection is a set of the data instances that the user has focused on. Boxer supports two active selections. Boxes show three quantities. First, the size of their set, or how many items they represent, as well as the intersection of their set with each of the selections. For example, each bar of a histogram bar chart is a box. Its height shows the size of the set. The height of the subbars show the amount of overlap with the selections. Note that Boxer uses the colors cyan and pink to represent the two selections. Many part-whole visualizations, where each glyph represents a subset of the data, can serve as a collection of boxes. In Boxer, we have bar charts, stacked bar charts, and matrix views. But we could also have used pie charts or tree maps. Boxer supports two active selections. We create the first cyan selection by left-clicking. We create a second pink selection by right-clicking. Here, we've selected the items correctly classified by a second classifier. This allows us to compare between the selections. The Selection Controls panel allows us a history of our selections. It shows how much the two selections cover the range of instances, and it shows how much the selections overlap. The selection controls allow us to perform set arithmetic on the selections. Here, we intersect the two selections, creating a new selection that is the set of instances that both classifiers got right. Boxer provides a number of views that can be used together to perform comparisons. We describe a few key ones. The overall performance view shows a stacked bar chart of a selected metric. We can choose accuracy, precision, recall, or a few others. The histogram view shows bar charts of feature distributions. A confusion matrix view gives classifier performance details. The list view shows specific data items in ways that emphasize their set relationships. The parallel metrics view helps with metric selection by showing the differences in how metrics rank classifiers. To help bar charts show and select small values, Boxer uses a circle to represent when a bar chart has a small bar that might be too difficult to see, but not quite zero. Boxer lets users place views and link them using selections. We demonstrate this power and flexibility in a simple use case. We have trained a classifier that determines whether a document was written before or after the start of the English Civil War. We are interested in whether short documents are easier to classify than longer ones. We select the short documents by unioning together their histogram buckets, and then select the longer documents by unioning those histogram buckets. In the selection performance view, we see that there is some difference in the performance between these two categories. We can perform a similar experiment to see if documents written close to the cutoff date are harder or easier than the rest of the documents. Here we see a larger difference between the documents written closer to the cutoff date and further from the cutoff date. Boxer is open source software. On our web page, you can try the system online and read user documentation. Scalability is a key challenge. In terms of performance, Boxer is implemented completely in browser. This created limits on memory and speed. However, we have used Boxers with datasets of 100,000 instances. It does become a little sluggish. Boxer's design scales well. The aggregate views are the same if the bars represent hundreds or millions of items. The dots help with dynamic range issues, but there can be issues with too many bars. Conceptually, our approach can handle much larger data. We can work with many instances through filtering and search. We are incorporating feature selection to handle larger numbers of variables. It is less clear how to scale to many different classifiers. Our work has a number of limitations. One is that we only have an in-browser prototype. Second, our system focuses on discrete choice classifiers. In the future, we intend to consider other types of problems such as regression or probabilistic classification. Third, our system is complex to use. While the views are simple, the user must figure out which ones to compose to achieve their task. We are working on addressing this with a guidance system. Fourth, we have not integrated Boxer into the development loop. In the future, we will explore feedback to the classifier construction process. To conclude, Boxer is a system for comparing the results of machine learning classifiers. Its key idea is to use set selection and display to allow for flexible comparisons. I invite you to try out the online demo. Thank you for listening.
Okay, we were competing about the mute button. I do the clapping for the rest of the audience. Okay, here we go. And
Hi.
Thank you, Michael, for the presentation. So there is a question, and actually Daniel brings up the question I also had in mind. What do you do if you want to compare more than two classes?
Okay, so the system is set up to do more than two classes. I only showed examples of two classes, but it handles multi-class problems well. The confusion matrices are, they scale. If you have a lot of classes, if it's more than, say, 8 to 10 classes, the confusion matrices get to be too big, so they're a little hard. All of the metrics have been tuned to work for multi-class. So we, for example, use the multi-class version of Matthews correlation or Matthews coefficient, depending on how you like to say it. So the system does work well for multiple discrete classes, but right now it is only for discrete choice classifiers.
Okay, cool. Which button do I have to click? I thought the very charming part was that you can select two classes with your two mouse buttons. What is for the third selection?
No, that's not two classes. I thought you meant classes as in terms of the classifier results.
Sorry, no, I meant the sub-selections.
Okay, so the selections, the idea of using two selections, first of all, that's one more than any other, or twice as many as than any other system. This was a difficult choice. What we realized was there's a trade-off that almost all of the time you can build complicated things using binary operations. So almost everything, if you want to union together 5 things, you can use it by doing union is a binary operation. So almost all cases really boil down to things you wanted to do with 2. When we thought about extending to 3, there's a really high cost in terms of the visual complexity of the system. Therefore, we didn't think it was going to pay off. So we believe that 2 is the sweet spot. with 1, it's too hard to do comparisons, and with 3, there's too much visual complexity, and with 2, you get the advantages of being able to do comparison and the ability to use set algebra to do more complicated things.
And to pitch to Eurographics, I also agree. So what is the triangle for graphics is essentially the two-way comparison for comparisons. I agree. Paolo had a question. In your opinion, how long would it take to get used to its complexity? And by its means tool.
That's a great question. When I've tried showing this to people, usually people get the hang of it in a few minutes. So that's one answer. The other thing is that even after months of using it, I'm still discovering like, oh, I could string this feature with that feature and connect this view to that view in a way I never would have thought of. So I'm, after however many months of this, I'm still finding new ways to use it. My feeling is that the key will be to have really good onboarding and guidance built in. So we actually are actively developing a onboarding and guidance approach to get people to be able to use it through documentation as well as in situ things to try and help you realize what the possibilities are for things that you can do.
That sounds pretty cool. Thank you again, Michael, for giving the presentation, writing the paper, and answering the questions.
Thanks for listening.
Okay, so we figured out that there was kind of a 50-50 vote on YouTube if the audio of Fritz was okay or not. We settled on the idea that it might be a phase shift between left and right that might confuse people. So we'll give it another try. So next to present is Fritz Lectures introducing peaks.
Visualization and computational biology, dynamics, multi-scale visual pattern exploration and genomics. We are going to present peaks, equal for interactive visual pattern search and sequential data, which uses unsupervised deep representation learning for similarity comparison. Visual searching for patterns in sequential data can be challenging. We will search peaks with large. The patterns are complex, while the query is difficult to formalize. To overcome these challenges, we need an effective feature representation that captures important visual properties for similarity comparison. Such features could, for example, be a number, height, or position of peaks, the maximum, minimum, or average value, or the horizontal. The feature representation of the data is typically defined by
Okay, feeling I got back on the stream here might be an indicator that the sound was not working or that something crashed. Feeling I got back. Okay, I think the logical next procedure is to just continue with the next talk, and we will see if we can maybe recode Fritz's video. I don't know exactly what the solution will be. But without further ado, I want to hand over the virtual microphone to Alex Boyerle, who's talking about classifier-guided visual correction of noisy labels for image classification tasks.
Thank you for tuning in to our talk. Today, I'm going to tell you something about correcting classification datasets. Modern classifiers need a lot of labeled data to be trained. However, generating these data labels is time-consuming, which is why this problem is nowadays often outsourced. For example, to less experienced crowd workers. Here, people that have no experience with the data itself are paid to generate labels. Sadly, this can introduce noisy labels, which in turn can result in reduced performance for the trained networks, or even the tendency to be biased towards these incorrectly labeled samples. Dedicated methods for correcting such noisy labels help correcting the dataset and thus improve classifier performance. We propose such a method. Our contributions in this paper are categorization of error types for classification training data, measures to identify candidates for these potential errors, and interactive visualizations towards resolving these errors. Our method is summarized in this picture, whereas gray boxes symbolize standard operations and blue boxes contain our contributions. With this, error correction begins with labeled data and goes all the way to productive use of the classifier. These steps will be explained in the following. We start our interactive visual approach towards correcting labeled datasets after labeling has been finished. This makes our approach independent from the way that labels are obtained. As we utilize the classifier to guide users to potentially incorrect labels, said classifier first has to be trained. To use samples where the classifier disagrees with the human annotation, we classify all dataset examples once. For the training process, users can decide when to stop the classifier training so that they can investigate more or less dataset examples. Other than this, neither the training process nor the classification of the training samples or the classifier itself is modified in any way. Thus, our approach can be plugged right into any classification pipeline. We then propose means to automatically guide the user to potential labeling errors. To do this, we identified 3 error types, which commonly occur in classification tasks. The first of these types is class interpretation errors, where users cannot accurately differentiate between 2 classes. As a score indicating the possibility of the presence of such an error, we look at how many items that were labeled as Y hat are actually classified as Y. The second type of common labeling errors we propose is instance interpretation errors, where only one single instance of the dataset is mislabeled. This can happen through a plain misclick, or when the labeler is not sure about that specific instance. A score for this type of error can be calculated when the classifier correctly classifies a sample, even though the label is incorrect. The score will be high for confident classifications, and lower if the classifier also assigned a high probability to the class the sample was labeled as. The third error type we identified is similarity errors. These errors can occur, for example, when dataset examples are scraped from online services. For 2 different dataset examples that are classified into the same class, the similarity error score can be calculated with common similarity measures, such as SSIM for images. Based on these 3 error types and their associated measures, we then propose a visual, interactive approach towards correcting these errors. This visual error correction consists of 3 steps: detecting error candidates, reasoning about these, and resolving them. In the following, we are going to show you how we implemented this in our approach. To support detecting error candidates, our visualization is based on the principles underlying confusion matrices. However, as we want to focus the user's attention to misclassifications of the network, where labeling errors can possibly be spotted, we rearrange our matrix. To bring attention to potential class interpretation errors, we further colorize cells based on their class interpretation error score. To make this guidance even more clear, we sort cells, first by label, and then within labels, depending on how many misclassifications they contain. As this reordering removes the context of these cells, we label them with dataset examples. In addition to this reordering and highlighting, we remove cells that do not contain data, as they also cannot contain incorrect labels. Now users can detect and investigate possible class interpretation errors by simply scanning the matrix from top left to bottom right. Let's look at this matrix and our implementation of this technique. In addition to reordering and highlighting cells to support the detection of class interpretation errors, we also show the instance interpretation error score distribution by horizontal red bars. Bars on the top of a cell mean that samples with a high instance interpretation error score are in this cell, while bars at the bottom mean that the network is not really sure about its classification of this item, and thus signal a low instance interpretation error score. For a third type of possible errors, similarity errors, we propose to overlay a duplicate icon whenever one of the cells contain items with a high similarity score. With this matrix design, we are able to provide the user a clear entry point for where to search for possible labeling errors. For class interpretation errors, they can scan from top left to bottom right. For instance interpretation errors, red bars mark possible errors, and for similarity errors, a duplicate icon is overlaid on a cell. Based on this information, users can decide to inspect a label classification combination in more detail and reason about possible errors. This can be done for class interpretation errors, as seen here, but also for similarity errors, through our similarity guidance, and for instance interpretation errors, where embedding projections are of great help and can, after resolving some of the items, isolate incorrect data points, as here, where a frog has been labeled as a cat. Being able to reason about errors is very important, as either the network can be incorrect and the human correct, or, for other cases, especially for similarity errors, some of the very similar items might be just data augmentations and are intentionally present in the dataset. Once reasoning about errors is done, our approach also directly incorporates resolving these errors. This can be done through confirming, but also changing a label for one or multiple data points, which is important for resolving instance interpretation and class interpretation errors. And at the same time, items can also be completely removed from the dataset to resolve similarity errors. Once data points have been confirmed, changed, or deleted, they are removed entirely from all calculations of error scores and from the visualizations we propose. With our approach of guiding users through our metrics visualizations for them to detect possible errors, reasoning about these errors using our in-detail cell visualizations, and directly resolving errors, users can clean up their dataset step by step and end up with a dataset ready for training. Our approach can be repeated until data quality is satisfying and the classifier and dataset go into productive use. In each iteration we show less samples to the user, as those that he already confirmed, changed, or deleted are not shown anymore. To test our approach, we implemented the web-based application that was just shown and which realizes the proposed visualizations. Using our approach, we were even able to find errors in the commonly used MNIST and Cypher10 machine learning benchmark datasets. We trained a simple classifier on MNIST and achieved 99.3% accuracy, which means, as in our approach only misclassified samples are reconsidered, we only had to look over 0.7% of the dataset, which equals to about 490 out of the 70,000 images. When looking at the classes 7 and 1, some samples are almost indistinguishable and could be an indication for different writing styles of these numbers. We also discovered individual samples that were incorrectly labeled. For example, this 3, which was labeled as a 5 in the original dataset. In Cypher10, we took a similar route and found several highly similar images of ostriches. Additionally, we found an instance of a frog that was labeled as a cat. All these findings have been made in original, unmodified datasets that are used for machine learning benchmarks. In addition to testing our approach on machine learning benchmark datasets, we also conducted a qualitative user study. Here, 10 participants were presented a corrupted version of the MNIST dataset, where we changed the labels to introduce 5 errors of each type we propose. We then trained a classifier and used our technique to visualize the results. This way, users had to look at only about 4,000 out of the 70,000 images in the dataset at maximum. After a short introduction, they were then given 15 minutes to correct the dataset they were presented. Finally, we also asked them usability questions to assess the usability of our approach. Our findings were that duplicates could be resolved pretty consistently through our duplicate guidance. Additionally, participants changed on average 2,902 images, of which only 27.5 were incorrectly changed. This equaled a correction of over 85% of the errors we introduced. When training a classifier after this correction process had been completed, the accuracy rose from 94.37 to 99.05% after only one iteration with our techniques. Additionally, users rated our approach as very helpful for correcting corrupted datasets. when after the study we looked at the samples we initially considered incorrectly changed, we found out that many of these labels are debatable in the original dataset. Our contributions in this paper are a categorization of label error types potentially occurring in classification training data, measures to identify error candidates by means of classifier response analysis, and interactive visual error guidance and correction by means of classifier result metric visualization. Our modular approach, which does not require modification to the network or the training process, could be plugged into any classification pipeline as is. For example, AutoML scenarios, where people upload datasets and let the system train networks for them. Here, error correction methods could be of great value. In the future, we imagine that adoption of these techniques to problems different from classification tasks and data different from images could be a great direction of research. Additionally, further investigation into error types could help the field advance correction techniques. Thank you for tuning into our talk, and happy error correction! Thank you for tuning into our talk, and happy error correction!
Thank you, Alex, for the presentation. I give the one-man clap here again. I think you will get some on YouTube as well. Very nice work. I have to ask the devil's advocate question. So imagine you have an industry-sized data set that is multiple millions, and you have a accuracy of 80%. So 20% is left to look through. So you probably look at 200,000, I don't know, up to 1 million of these things. Does your approach still scale?
Yeah, that's a very good question. So yes, this is definitely a limitation. At maximum you have to look at the amount of images that are misclassified. But through our guidance, I would argue that still we can guide users to more severe cases, so that you don't always have to look at every sample that was misclassified. So that in that sense, it could be used, but yeah, this is definitely a limitation. Yeah.
Cool, thank you. There was also a question from Lars Lensen. Can you comment on the workload for corrections? So how long did it take for which data sizes? So essentially, like, how many corrections per minute can you do?
So I can only really speak about this from the point of our user study, where we corrupted an MNIST dataset and participants had to correct it. And they had like 50 minutes to do this. They had not used the tool before, so this was all new to them, and they were able to correct many of the labels. And I don't know the exact number, but they changed in this 15 minutes to change many of the labels of the data set. So I would say the time needed to correct the data is not a really huge problem. If you have like a limited number of samples to look at, if you don't have to scan through all the data set again. It definitely cuts down the time from comparing to go through the data set like in a file explorer or something like that, where you have to look at many more examples.
Have you considered of utilizing the model itself to get you a little bit more, a better guessing of what you should look for? So I mean, there are these all these methods that allow you to do to show you to focus on which part of the image decision was mainly focused for a specific unit, etc. So, like, did you consider adding some kind of saliency mapping features, etc., to say, okay, maybe look at the dog's ear, maybe that's why I misclassified it?
So I didn't mention this in the talk, but we actually do something like that for the TSNE projections or the UMAP projections. That we have to like scatter out the data and create clusters. We don't do that on the direct images, but we do that on kind of saliency visualizations, as you said. So the images are already grouped kind of by what the network sees in them. Yes.
Cool. Thank you very much for presentation and discussion. I think from what I can read, everyone says looks like a very useful tool. I hope it's open source.
Thanks. I can make the code open, but it's like really researchy.
No excuses. Okay, we will give now the stage to Fritz's video again. So I see Fritz becoming slightly more nervous here. But so we might have a solution, and fingers crossed this works. If not, you might see me again in some seconds. I hope not.
Scale visual pattern exploration in genomics. Today I'm going to present peaks, a tool for interactive visual pattern search in sequential data that uses unsupervised deep representation learning for similarity comparison. Visually searching for patterns in sequential data can be challenging when the search space is large, the patterns are complex, or the query is difficult to formalize. To overcome these challenges, we need an effective feature representation that captures important visual properties for similarity comparison. Such features could, for example, be the number, height, or position of peaks, the maximum, minimum, or average value, or the noise level. The feature representation of the data is typically defined up front. While this is useful for finding specific patterns, it requires a deep understanding of the data and often does not generalize well. For instance, in this example from biology, analysts often want to determine the number of peaks, as those act as proxies for biological events. But without domain expertise, it's hard to tell whether we should count 5 or 7 peaks in this example. Also, what if we want to capture peaks of other shapes? To improve upon existing pattern matching techniques and provide a generic solution, we have developed a convolutional autoencoder model for unsupervised feature learning. Given a region of sequential data, the first part of our autoencoder model learns a latent representation that the second part of the model uses to reconstruct the input data. By having a lower dimensional latent representation, the autoencoder is forced to learn an abstraction that captures the important visual features of the data. Additionally, to support interactive visual pattern search, we not only need a good matching technique, but also a system that is able to adapt to the user's perceived similarity. We have developed a system called Peaks that uses our novel representation learning technique and combines it with an active learning strategy to allow users to interactively train a classifier that identifies the important visual features using binary relevance feedback. Now, the first question we have to answer is whether our proposed representation learning technique is able to capture these important visual details of the data. Here we can see the reconstruction results for a genomic assay called DNA sequencing. Each column shows 3 examples of a particular size, but ultimately each region is aggregated into a vector of size 120 before being encoded with our convolutional autoencoder. For each example, the original data is shown in white, the reconstruction is shown in blue, and the difference between the two is shown in the pink-blue chart. Overall, we can see that the autoencoder provides a smooth reconstruction of the input data and is able to encode most of the salient visual features. We also see that as the size and pattern frequency increase, the reconstruction loss increases as well. Numerically, we see the same picture. The R-square scores, which tell us how much variability is explained by the reconstruction, decreases from 0.98 for the smallest region to 0.78 for the largest region. But reconstruction wasn't our actual goal, so you might ask, is the learned representation also useful for similarity search? And the answer is yes. We compared our technique to a set of 6 other commonly used techniques for similarity search in sequential data. To do so, we defined a set of 9 diverse search patterns, which are shown here in the top row. For each of these search patterns, we extracted the 5 most similar regions found with our technique: Euclidean distance, symbolic aggregation approximation, dynamic time warping, normalized cross-correlation, UMAP, and a tool called tsFresh. Looking at some of the details, we see that each of the other techniques can fail to capture important aspects of the target pattern, as highlighted here with these pink boxes. And while no technique provides perfect results, our autoencoder model is able to consistently capture more important visual aspects. And we were able to confirm these anecdotal results in 2 user studies on Amazon Mechanical Turk, where we found that the 5 search results from our technique are perceived significantly more similar to the target pattern than the results of any other technique. But so far, we've used all features or dimensions of the learned representation equally for similarity comparison. However, the notion of similarity can vary by person and search query. For instance, sometimes only the number and shape might be important, while other features like the position and magnitude might be irrelevant. To provide a generic approach for visual pattern search, we built peaks around an interactively trained binary classifier that operates in the learned feature space and tries to identify the features that are important to the analyst for a given query. The training data for the classifier is provided interactively by the analyst in form of binary relevance feedback. And so ultimately the goal is to train a classifier that finds regions in the sequential data that are perceived similar to the search query. Since many datasets are large, we additionally need a sampling strategy that focuses the interactive labeling process on a subset of regions that are useful for training this classifier. In this regard, we developed a sampling approach to select regions which the classifier sees as uncertain, which are located in dense neighborhoods, and are relatively close to the search target. The intuition behind this sampling strategy is the following. Labeling uncertain regions in dense neighborhoods is likely to improve the learning effect and thus make the labeling process more efficient. The initial focus on regions that are relatively close to the search target will ensure some level of similarity between the samples and the search target, which can help to concentrate the labeling process on meaningful pattern differences and also keep the analyst happy or satisfied during the labeling process. Now let's take a look at the user interface to see how all these aspects play together. The interface of peaks consists of 4 main components. At the top is the query view, which shows the region defining our search query. The view is pan-unzoomable to allow free exploration of the entire dataset. Below the query view is a list view which represents different regions of the data for comparison and labeling. And depending on the tab, the shown regions here are either selected by our active learning sampling strategy for exploration, or they're defined by the results of the trained classifier for exploitation. For debugging, it's also possible to look at previously labeled or manually selected regions. Importantly, every region here features 3 buttons for labeling them as either matching the search query, not matching the search query, or being inconclusive. At the top of the right sidebar is the embedding view, which shows a 2D embedding to explore regions based on their latent representation coming from our autoencoder model. In this view, every region is represented as a dot and color encoded to its label, where blue indicates a positive match and pink indicates a negative match. A secondary light gray to blue color map encodes the dots by the classifier's prediction probability, where dark blue indicates that the classifier is certain that this region matches the search pattern. And finally, at the bottom right is the progress view, which visualizes the classifier's uncertainty, the overall change in the prediction probabilities, and the convergence or divergence of prediction probabilities for every training to help users determine when to stop the labeling process. Here the inner and more saturated bar is relative to the set of already labeled regions, and the outer bar is relative to all regions of the data. Now in the following I'll show you a brief example of how peaks can be used to build a classifier from scratch. In this example we're looking for pairs of overlapping but slightly shifted peak-like patterns. In order to build a classifier for our search query, we need to provide feedback to the system in form of binary labels. We start labeling regions selected by our active learning sampling strategy as either matching our search target, not matching our search target, or being inconclusive with clicks on the corresponding button. At the end of the initial sample set, we'll train our first classifier and then receive a new set of samples. And as we continue labeling regions and training classifiers, the progress will keep us informed about the state of the learned classifier. For example, we can see that the uncertainty is gradually decreasing. Now, to gain an overview of all regions, we take a look at the embedding view. Using the prediction probability color map, we can identify neighborhoods of region that contain potential matches. We could use the embedding view to explore these regions in detail using the lasso tool, but for now let's turn our attention to the results to assess the current performance of our trained classifier. Besides just browsing the results, we can further improve our classifier by continuing to label regions to confirm true positive predictions and to inform the classifier about false predictions. After several rounds of labeling and training, our labels can disagree with the classifier's predictions due to inconsistency. Peaks notifies us about such conflicts to encourage resolving these issues. For instance, here we fix some incorrectly assigned positive labels, which we do not consider matches anymore. Once we are happy with the current results, we can explore the entire dataset in the query view. To guide this exploration, the query view visualizes the prediction probability as a light gray to dark blue heat map, where again dark blue represents strong matches. This way we can quickly find other regions in the sequential data that exhibit similar patterns to our search query. We evaluated the usability and usefulness of peaks in an in-person user study with 8 computational biologists on a simulated dataset, and first of all found that peaks is easy to learn and use. A 15-minute introduction was sufficient to enable the participants to successfully build and refine pattern classifiers. But more importantly, we also found that on average, the classifier's performance was higher when trained on the experts labels compared to training the classifier on the ground truth labels of regions sampled with our active learning sampling strategy, which indicates that the expert-steered training can be more effective than an automatic approach. To conclude, we showed that modern machine learning techniques can be used to improve interactive, user-driven exploration, and we hope that others will use peaks with their own data and maybe even extend it with new encoder models. For more details, please refer to our paper, and if you want to try peaks yourself, please visit peaks.lectures.de. Thank you.
Cool. Thank you, Fritz, for the presentation, and again, the usual one-person clap. We have some questions coming up from YouTube, and I just forward them to you. Number one is from Marco. What kind of DR models do you use for the 2D projection embedding?
So we use UMAP for that.
Okay, that was a quick answer. Was also a quick question. Would it be feasible crowd and or gamified label? Oh yeah, would it be feasible to do a crowd or gamified labeling, or as a method to do this, as crowd labeling or gamified labeling? Which probably for us. I'm sorry.
And that's a really interesting question because definitely technically it's possible. There's nothing that prevents you from doing that. I think one interesting thing to look into is how consistent are the labels between different labelers. So one of the things that we learned in the user study that we did with the biologists is that, when the pattern is simple, they mostly agree. So we tell them to look, for example, for 2 overlapping peaks or a peak in one track and not in the other. But still, people perceive written instructions very differently. So there could come up a lot of conflicts during the labeling process. And that would be really interesting to look into to see how consistent like what do people think of when you tell them find for a search for a specific pattern? I hope that answers the question somehow.
I think for me it did, and I hope for the rest as well. We'll see in a second in YouTube. I have two devil's advocate questions. Number one. It appears when I look at the system itself in action, it appears like a relevance feedback search system. Yeah, so you do an initial search, you give relevance feedback, and the search is accordingly adapted. What do you think is the additional add-on to a relevance feedback search that is potentially enabled by using this active learning machine learning model?
So I guess, the main thing that we wanted to find out is if this works for non-natural image data. So there have been systems that use exactly such a relevance search approach for natural image data, but none of this existed for these rather abstract peak-like patterns. The other thing that we wanted to test with this is, and I didn't really go into details in the paper, but please feel free to talk to me afterwards if you're interested, is that we can work with multiple tracks. And it wasn't quite clear if that works just out of the box. So you can stack multiple data sets on top of each other and search for patterns across these different systems. But in the end, it's a relevance feedback search system, just enhanced with an autoencoder. So you don't have to think up front so much about what feature you want to extract.
Yeah, and it looks pretty amazing, pretty interesting. Speaking about that, you showed an example for a very specific biology domain, but I can also see that you could do something like general detection or outlier detection in time series, etc. Do you see this capability as well, or do you see limitations in trying to apply this more general?
So there's no basic limitation in that sense. I think the main thing to test is how well does the autoencoder, or whatever encoder model you use, is able to capture the features of your data. So we were able to see that for the data that we have, this spiky peak-like data, it works pretty well. Of course, if your data looks very different, so if you have time series data where maybe the differences are very marginal, you might have to test first how well your autoencoder works. But other than that, the main limitation, I think, is you cannot search for, let's say, a random noise, at least not with an autoencoder, like a convolutional autoencoder, because the autoencoder gets it doesn't get rid of the noise, but it doesn't encode the noise. So if you wanted to detect something like different noise levels, that wouldn't work. But then that might not even work with a human, because we also, as humans, not very good at detecting different noise levels.
Cool. Yeah, that sounds pretty cool. Again, thank you very much for the presentation and for answering the questions. I also want to go over to this slightly more sentimental part now. Thank you all for taking part in the session, especially the presenters. Yeah, Fritz, super cheap, Alex and Michael. I hope everyone who was listening and watching the presentation enjoyed it. I'm pretty sure you can reach out to all the authors if you have further questions. And with this, have a good morning, afternoon, evening, or night, wherever you are. Thank you very much. See ya.